Okay, so let's get started. As I said, we looked at one example problem related to convergence, and then we looked at the notion of intervals, open set, open interval, etc. And then we also looked at closed set, a compact set, meaning closed and bounded is compact. And then we
Sir,
start. Yes,
you have not shared the screen.
is it? Okay, I'm sorry. Let me share the screen. Now, is it visible? Okay.
Yes, sir.
Okay. Yeah. So then we looked at two important notions called infimum and supremum, right? So infimum, you can think of it as a proxy for minima, and supremum as a proxy for maxima, right? So whenever you don't have maxima, supremum always exists. So you need not worry about whether maxima exists or not. So you can always say, I'm going to find the supremum of a function or a supremum of a set, and so on. Okay, it's matter of convenience for us. So what is the Suprema? Can somebody tell me? Yes, you with the yellow shed. Yes, you only. You had a lot of discussions, right? Can you tell me what is the Supremum? The least upper bound of a set is Supremum. What is infimum? Greatest lower bound is a okay, good. So then we looked at what is known as continuous functions, right? So what is a continuous function? Essentially, you take a point, and I want to say that a function is continuous at that point. What you do is you take any sequence that converges to that point, then the corresponding function f of xn should also converge to f of x naught, right? Then we say that the function is continuous at that point, and if it is true for every point in the domain of the function, then we say that the function is continuous. Okay. Then we looked at a small set of properties regarding continuity. So if you add two continuous functions, you get a continuous function, product is continuous, and so on. Okay, so then we started looking at some notions in linear algebra. So essentially, we looked at the notion of a vector space, right? So what is a vector space? How do you define a vector space? So that's what we started in the last class, right? So what is the motivation? So you just start with two-dimensional, let's say the usual vector that you would have studied in your pre-university, and see what are the kind of properties that the vector should satisfy. If you take any two vector, add them, you get another vector. You scale it, you get another vector, right? For every vector, there is a negative vector. When you add them, you get a zero vector. And what else? It doesn't matter how you add vectors, right? V plus u plus w, which should be same as v plus u plus w. And when you scale the sum, it's the sum of the scaling. Alpha times u plus w would be alpha u plus alpha w. So these are some of the properties of a usual vector, right? Is that clear? Everyone? You need not remember what a vector space is. No one, right? So you just have to think of usual vectors and see what are the properties that those usual vectors satisfy. That will be the definition of a vector space. Instead of writing R3, I can replace it with something else. Let's say V. Instead of taking a number alpha, you can take a complex number or a real number. Okay, so alpha here that I have chosen, I have chosen it to be a real number. That means I'm going to scale or compress or elongate a vector, right? So I can as well consider a complex number and then multiply the vector by a complex number. So it doesn't matter. But for now, let's stick to real. So without loss of any, I can either choose R or C without any change in the treatment that I'm going to present now. Okay. Okay, so now what is the advantage of abstracting out or collecting the properties of vector and generalizing it? That's called abstraction, right? So what is the importance of abstraction? You might have studied abstraction in mathematics, right? So they don't do all this. They will say we say that a set V is a vector space over a field F if V plus if V belongs to V and U belongs to U, then V plus U belongs to V and so on, right? So that's called abstraction, right? You take certain properties that you can observe and then try to see whether there are any other objects which satisfy these properties, right? So what is the convenience here? Let's say you are studying something in R2, right? Two dimensional. I haven't defined what dimension is. let's suppose that you are studying vectors, the usual vectors. Then I want to generalize it to R3, that is a three-dimensional vector that you can observe, right? Then I need not write another book on that, and R4 I need not write another book, and so on, right? So I can just write one book. The V that you consider could be R3, R2, or set of continuous functions from 0, 1 to 0, 1, etc. Right? Is that clear? Okay. So now, in the last class, we looked at a few examples. So set of all 2 cross 2 matrices. Matrices are quite different from vectors, but aesthetically, right? So I can do one thing. I can take, for example, a matrix A, B, C, D. I can always do a mapping, right? An invertible mapping. What is that mapping? I'll do A, B, then I'll do C, D, right? This is invertible. Do you agree? I mean, you know how to go back, right? So given a vector, you know how to form a matrix, and given a matrix, you know how to form a vector. So now this is in what? In R. I mean, you can think of R4, right? Because you have 4 entries intuitively. Now, every 2 cross 2 matrices, I can map it to a vector in R4, right? That's why it's not very surprising, right? It's just aesthetics that makes it look different. That's all. But whereas the other example, right? So set of all polynomials, it's definitely, I mean, you cannot, polynomials are functions, right? You have been plotting polynomials, but can that be vectors? Well, I can think of those as vectors. Why? Can somebody tell me why one can think of set of all polynomials as, or each polynomial in that set as a vector, and the set of all polynomials as a vector space? Why? Huh? Multiplication of 2 vectors. Hmm? But that has nothing to do with what you. So what you are saying is, for example, I can replace this by, you are saying a naught, a1, a2, and this is 1 x squared, right? That's what you are saying. No, I mean, that's not the right thing, right? So this doesn't resemble your usual vector. Do you agree? R2, I know, I mean, this is a straight line with a point, and it's pointing in some direction, right? So it's definitely not that. You can think of it as an algebraic object, or you can think of it as a function, right? So it's a strange object, but still you can think of it as vectors. I mean, a lot of properties that a vector satisfies will also be satisfied by this. It has its own advantages. Okay. So why is that? For example, you take any 2 points in this P. So what do you mean by taking 2 points in this P? You know what do you mean by taking 2 vectors in vector space, right? Very clear. But what do you mean by taking 2 points in this space P? You take 2 polynomials, right? For example, a0 plus a1x plus a2x squared is one polynomial. b0 plus b1x plus b2x squared is another polynomial. When you add them, what do you get? a0 plus b0 plus a1 plus b1 times x squared plus a2 plus b2 times x, a1 plus b1 times x plus a2 plus b2 times x squared, right? It's another polynomial wherein the coefficients are numbers like this, and therefore it also belongs to P, right? That means if you take 2 polynomials, add them, you get another polynomial. It's closed under addition. You scale it by a number, it doesn't change, right? It's still a polynomial of second degree, right? So it still belongs to P.